Hey everybody, today we're doing the second video on product integrals. Really, it's just geometric calculus altogether. So in the last episode we showed that the product integral of f of x to the dx is equal to e to our regular integral of ln of f of x dx. Alright, so we're going to apply that. So the homework question was to solve this. What is the product integral of x squared to the dx? And we're going to figure out what that is. So yeah, let's just dive right into it. So this is going to be equal to e to the integral of, oh wait, let me make that integral sign a little neater. Integral of ln of x squared dx. Alright? And so we can actually just make this equal to e to the 2. We can move the 2 to the front, and actually we can move it all the way out. Times the integral of ln x dx. And we just need to know what the integral of ln x is. So I've made a video on this, but let me just do it really quickly. So integral of ln x dx. We can use integration by parts. So u du, we can put v and then dv. So u is going to be ln x, because we don't know how to integrate, obviously, at ln x, unless you do, obviously, but we don't here. And so the derivative is going to be 1 over x, and then dv is just going to be 1, integrate that, and we get x, alright? So we can actually just plug it in, use this information to plug it back in. So u dv, so it's just going to be ln x, wait, let me make that whole thing a little better. We have this is ln x minus the integral of v du. X times 1 over x is just 1, so it's just dx. So this is x, this is ln x, so wait, it's x ln x, yeah. X ln x minus the integral of dx, so x ln x minus x plus c. And that is our integral of ln x. So this is equal to e to the 2x ln x, and I'll do a minus 2x, and then plus c. I mean, it's 2c, but it's still just a constant, so it doesn't really matter. And so we can notice that e to the ln x is just x to the 2x, and then this is over, right, because we're gonna, whenever we do e to the something minus something, that's just gonna be like dividing by, just exponent rules basically, over e to the 2x, and then times e to the c. I'll put this e to the c out front. E to the c is just itself another constant, so I'm going to label it capital C. And then we have that this is x over e to the 2x, and that's it. That is our product integral of x squared. And you can actually replace this 2 with an n, and that's going to give you the product rule. So the product integral of x to the n dx is equal to c, a constant, times x over e to the nx. So pretty kind of similar. You have this e here, which is a little different, and a little different to the normal product rule, but it's pretty cool nonetheless. And it should make sense that you're multiplying by a constant, because whenever you in additive calculus and normal calculus, you just add a constant. Here you're multiplying by 1 because it's multiplicative. So now let's try to go from here back to here. So what we're going to do is we're going to have to generate a function to get our derivative back. So what we want is some function, we'll call it f star of x, as our geometric derivative. So this is our geometric derivative. So basically, we want that the product integral of f star of x to the dx is equal to some constant times f of x. And actually we want the added condition that it's going to be the absolute value of f of x, because whenever we plug it into ln, the natural log, it's going to have to be positive. So we have to have it be a absolute value here, okay? So what we want is basically just some function. Let's replace this with e to the integral of ln of f star of x dx. I'll just put parentheses around this. this is equal to c times this. So here I'm just replacing this with this definition, not too difficult here. So now we want to isolate f star to figure out what that is. So we can say that this is so we can take the natural log of both sides, right? So we get that this is that, dx is equal to ln of c plus, ln of c plus ln of absolute value of f of x. Alright? This is ln of this is equal to this, just by multiplication, because this is multiplying, so we can add these two. And so if we take the derivative of this, we get that this is ln of f star. So we're getting really close. And we get rid of the dx, of course. This is equal to derivative of the natural log of c. This is just, c is just a constant, ln of c is also just a constant, so that goes to 0. Derivative of the natural log of absolute value of f of x is going to be, so actually let's ignore the absolute value bars for now. It'll come back later, but just know, let's just ignore this, but that is relevant in the future. But for now, we can kind of just pretend it's not really there. So then basically, so derivative of that is going to be f prime of x over f of x. And then if we want to isolate this, this is going to be, e to the f prime of x over f of x. And this is our geometric derivative. So that's pretty cool. And so we can just plug this back in here. So let me actually do that. So let me use the operator, instead of d over dx, let me use d star, capital D star of x squared as my operator, d star. That's our geometric derivative. So we're going to plug this into our formula. So let me say this is equal to e to the just the normal derivative of f prime, which is x squared. So that's going to be 2x over x squared. And this is equal to e to the, I'm sorry, not of x squared. It's going to be of our original function. I'm like, what am I doing here? No, but we're plugging our original, whatever we got as our answer back in, and we want to get back x squared. So we're going to get, c times x over e to the 2x. Yep, so this was our function. And we have to use implicit differentiation to figure this out. So the c will go away, so let's just kind of pretend it's not there. So we get this is y equals x over e to the 2x. And the reason we use implicit is because we need this f prime up here. So, let's just do it that way. So we can say that this is ln y is equal to 2x ln of x over e, and then ln of x over e is just ln x minus ln e, so then we do it that way. So this is 2x times ln x minus ln e, so ln e is just 1, so I'll just leave that there. So we can actually say that this is 2x ln x minus 2x, just by, again, some more manipulations here. And then we can basically just take the derivative of both sides. We get that this is y prime over y is equal to 2x times the derivative of ln x is 1 over x, so 2x over x, which is just 2, plus ln x, so it's just 2 ln x, minus derivative of this is just 2. So we get that this is y prime equals, we can multiply this y, so x over e to the 2x, multiplied by 2 minus 2 is 0, so it's just 2 ln x. So we can plug this back in into our original function. So let me erase this now. And so basically, what we get is, d star of c times x over e, let me just get rid of the c, to the 2x, this is going to be equal to e to the f prime, which is this. So this is x over e to the 2x times 2 ln x over our original function, which was x over e to the 2x. And so we can cancel this and that out, right? We can just, because they're the same. So this is going to be equal to e to the 2 ln x. E to the ln x is just x, and it's squared. That's it. So we get the original function back. If we had the c here, it would also just go away, because it's just how the rules work. But yeah, we can generalize some rules in the next video, find some more things. And if you have any questions, then just feel free to ask me in the comments. I think I probably went a little bit quickly in certain parts, but I hope that you kind of understand the premise of what we're doing. So yeah, main takeaways is the obviously this formula, and also the fact that d star of f of x is equal to e to the f prime of x over f of x. And d star, of course, this is just, again, equal to f star of x. So yeah. So yeah, thank you all for watching, and I'll see you in the next video. Bye guys.